Hello! Welcome to Lecture 3, which we're going to be talking about rocks and how they form. So first off is, what are rocks? As we went over in our minerals class, minerals will come together to form rocks. Generally, a rock won't be made from one mineral, but many. Occasionally, though, you do get one that is generally one mineral, like olivine, or gold, or silver, but they'll generally have other minerals in there with it that it has formed with. So, what are rocks? An amalgamation of minerals. Some rocks are one mineral, but generally they aren't. These are olivine, gold, and silver that are great examples of a one mineral rock. However, they usually have something else mixed in. So these are what you need to remember about what a rock is. So there are different types of rocks. There are different types of category. You have metamorphic rocks, which are formed due to extreme pressure and temperature. They can occur during mountain building or during a Wilson cycle. And we're going to go over what a Wilson cycle is in a couple lectures when we talk about tectonics. Then we have igneous rocks, which are formed by magma or lava. So magma is molten rock that is inside of the earth, whereas lava is when it comes outside, like during a volcanic eruption. Okay, they can be intrusive, so inside of the crust, or extrusive, on top of the crust in origin. And then we have sedimentary rocks. These are formed from the accumulation of sediments which are eroded from igneous, other sedimentary rocks, or metamorphic rocks. So as I mentioned in our last class, in our first class, we really like to explain things in the form of cycles in science. So this is the rock cycle, and we use it to explain how rocks are formed and how they change. Under the correct conditions, a rock may change into any of these other rocks. So a igneous rock can become a sedimentary rock, or a metamorphic rock, or another igneous rock. The rock cycle technically begins with magma. So this is lava, which is what magma is called when it reaches the surface of our planet. Magma forms in a part of our Earth, one of the layers that are called the asthenosphere and the lithosphere. Okay, so heat rises in the asthenosphere. It'll usually melt the lithosphere, or the boundary between the two, and then because this material is really hot, it's less dense than the surrounding rock, so it'll rise just like oil and water will. So this will end in two scenarios: the magma erupting and become lava, or cooling and staying just underneath the surface. So cooling is the solidifying or crystallizing of lava and magma. So when exposed, igneous rocks will undergo something called weathering. This will turn them into sediments. These will then be transported with water, wind, gravity, or a whole other variety. And once it is deposited, it will be compacted or cemented, which is known as lithification, to form a sedimentary rock. And it looks like this. So the first thing we start out with is an exposed rock, which then gets weathered, okay? And it becomes sediments, which then gets transported, deposited, and then it will go through lithification to become a sedimentary rock. After which, it can go through metamorphism and become a metamorphic rock, melt and become an igneous rock, or start all over again, becoming another sedimentary rock. Thus, the rock cycle. Rocks themselves are not unchanging. They are constantly under pressure, melting or undergoing erosion. The sand on the beaches down in Florida are due to erosion, and most sediments will actually travel in water and get transported to oceans. However, from what we can see from this rock cycle, it is not a perfect circle. The cycle itself is driven by the Earth's internal heat and external processes, so this could occur out of order. Some igneous rocks can even get remelted and become new igneous rocks, just like a metamorphic rock can get reheated and undergo pressure and become a new metamorphic rock. So igneous rocks are formed by magma. An intrusive igneous rock, which is a rock that is underneath the surface, is called plutonic. And if it's formed by lava, it is known as an extrusive igneous rock, or volcanic. Although we hear a lot about volcanoes and their effects, most lava is usually trapped underneath the surface of the Earth where it cools. These will form what we call plutons or laccoliths, which are plutonic igneous rocks. These will form from what we call magma chambers, and these can end up being reheated and melted as new magma enters the chamber. Most of the time, these plutons will be exposed by uplift of the Earth, like mountain building, or if the area around the magma becomes eroded. This occurs because igneous rocks are actually very strong, so they don't erode as fast as, let's say, sandstone, mostly because they are pretty hard compared to the sediments around them. So examples of this are Mount Washington, Stone Mountain, Mount Rushmore, and the Black Hills in South Dakota, and Yosemite National Park. So this is a laccolith. This is what it looks like. This is what we call uplift. Okay, so this at one point may have been, let's say, 200 feet under the surface that we stand on, but meaning that the surface was actually up here at one point, and all around it was sandstone, and it got eroded, and once all that pressure got removed, it kind of lifted up. Almost like when you put your hand on Play-Doh and you push it in, it'll slowly push back out as you lift your hand off of it. So here we have a laccolith that is eroding. This is Mount Washington in New Hampshire. It's part of the White Mountains. It's one of the tallest mountains on the East Coast. They will actually have blizzards in the middle of summer, so it's cool. And this is Yosemite National Park. So this in itself is a laccolith. So magma itself is not one giant liquid. Magma is formed from what we call partial melting of the lithosphere or asthenosphere, which many of you know as the mantle. This means that it's not entirely liquid. It's only slightly liquid. So think more along the lines of chunky peanut butter. Okay. As the system cools, minerals will form and separate out, following what we call Bowen's reaction series. So magma will cool slowly, right? So it doesn't, again, magma isn't just one liquid thing. It's got liquid plus gases, which is what we call volatiles, and solids like crystals. And as the magma will pond within the crust, it will be at a very high temperature, but it will start to cool as it sits still. Okay, this allows for minerals to begin forming. Well, why does it cool? The surrounding rock is much colder than it is. Remember, it's really hot, it's liquid. Rock around it is solid, so it must be cooler. So the heat kind of gets absorbed into the surrounding rock as it cools. So as the system cools, minerals will form. They kind of separate from the magma in what we call Bowen's reaction series, which is basically as minerals form, the chemical composition of the magma begins to change, allowing for more felsic, basically silica-rich minerals to form. And this is what Bowen's reaction series looks like. As the temperature begins to drop, different minerals begin to form. So olivine will form first. This is what we call an ultramafic rock. So it's very dark. It's a dark mineral. Okay, remember, lots of magnesium and iron. So as these darker minerals start to form out, you end up with the remaining elements being able to form lighter minerals or felsic minerals, such as quartz. The rate that the magma cools will also influence the size of the crystals present, which creates texture. Magmas tend to cool slower, forming larger crystals, and these can also be cooled quicker or quenching, forming glassy rocks. Minerals that form at the same temperature or pressure range tend to be associated with the same igneous rocks. In addition to volatiles like water, this also determines what sort of minerals can form. So with water involvement, you can get minerals that need water, like amphibole and biotite. Volatiles can also decrease the temperature of the magma and the pressure that a magma can begin to crystallize. So let's say a magma needed to be at 1000 degrees Celsius and at a pressure of 800 bars. Well, now that water is involved, both the temperature and the pressure necessary for crystallization to form is now less, meaning that it can start crystallizing at higher temperatures or higher pressures. How much oxygen in the magma and how viscous it is can also be affected by volatiles. Formation and separation is called magma differentiation, and it's a formation of secondary or third magma, we're going to call it, from a single parent. Okay, so you'll have magma 1 and it starts to cool and minerals kind of fall out. They differentiate, they separate from the magma, and now we have another type of mineral form. It falls out. And now our magma, we have our third magma that formed. And then as they separate out, the magma becomes more and more silica rich or felsic. Okay, so you go from a parent rock, which has partial melting, you'll have a more felsic magma, and when it crystallizes will form rock 1, and then the residue has more silica in it, which will form rock 2, and then your residual liquid is even more silica, so then you'll get rock 3, etc., until it is all solid. So during this separation, the composition will change. So again, you get more silica-rich rocks as you move up, okay? So let's say our magma body starts down here, yes? It's really hot, there's a lot of magnesium and iron in it, and we have one eruption, right? So these eruptions are going to have a lot of iron and magnesium-rich minerals. Well, now crystallization has begun in the magma chamber. So now we have magma 2, which is going to make rocks that maybe are more intermediate. You're going to have some silica, more silica in there. So you're not just going to have these very magnesium iron rich rocks. You're now going to have kind of in the middle. You're going to have some magnesium and iron rich, some are have more silica in them. And then we have another stage of crystals. And so now we're going to get liquid 3. And this is where we're going to see our more explosive volcanoes. You're going to see, but right now we're going to talk about textures. And to understand that, we need to talk about extrusive and intrusive types of rocks that form, okay? So what we have here on the left is known as a strombolian eruption. On the right, we have a lava fountain, and in the middle is a lava flow. So each of these will cause different types of rocks to form. Water, lots of purpose in volcanic activity. It can cause bubbles to form. It can cause explosive eruptions. If water is not originally part of the system, and let's say it's underneath a lake, and then an eruption starts and that lake all drains down, it will super explode. Or you can have eruptions that are very calm, like in Hawaii, which we call effusive. But when lava cools, it tends to cool quickly. And this forms rocks with smaller crystals than magma. Okay? So when lava is quenched or gets cooled very rapidly, it will form volcanic glass like obsidian. The composition here is mostly silicate minerals like silica, oxygen, and aluminum, calcium, sodium, potassium, magnesium, and iron. Okay? These make up 98% of most magmas with additions of trace elements. Trace elements are elements that aren't really important, but they might change the color of the mineral. So for example, quartz is multiple colors because of what trace element is present. Okay, so if iron is present, it'll be red, versus if radiation is present, it'll be smoky quartz, so be wary. If you have magnesium or titanium, it'll also change the color if it's a trace element, not a major element. Okay. So this leads to two types of composition, light silicates and dark silicates. So remember, silicate minerals are minerals that are predominantly made with silica. Silica is the base here, so like SiO2, like quartz, okay? Or SiO4, sorry. So dark silicates are richer in iron or magnesium. They'll have a much lower amount of silica than your felsic material. So they're going to form basalt. Remember that black rock that you'll see in Hawaii? That is a basalt. Okay, and these form olivine, pyroxene, amphibole, and biotite. And we're going to see all of these. We have seen at least two of these in our mineral lab. Okay, light silicates contain greater amounts of silica, potassium, sodium, and calcium. So they form quartz, muscovite, and feldspars. So feldspars are more abundant mineral group. They make up 40% of most igneous rocks. Okay. And depending on what type of feldspar you have can actually determine the color. So sometimes feldspars are pink and sometimes they're white. So how can you tell if a mineral is dark or light other than the color? So you can look at it like this. The increasing amount of silica, the paler it is. So granites tend to be made up of muscovite, quartz, feldspar, a little bit of plagioclase feldspar, and sometimes biotite and amphibole. They'll have a little bit of dark colored minerals in them. And this is how you know you have a lighter rock. Okay, so this is going to be a felsic rock. And then you have your intermediate rocks. where you're going to have some quartz and some potassium feldspar, but you're mostly going to have plagioclase feldspar, which is white, biotite, amphibole, and pyroxene. These are our darker minerals. Okay, and as you get darker, you end up with more and more darker minerals, so like basalt to ultramafic. Ultramafic's pretty much all olivine with some pyroxene and some plagioclase, whereas basaltic, you're going to have olivine, pyroxene, amphibole, and plagioclase. So granitic or felsic rocks are feldspar and silica, basically, quartz. They'll contain about 10% of dark minerals, but they're generally 70% light minerals. And the major part of the continental crust is granite. And we've all seen granite, whether it's on the side of the road, being used for decoration in people's gardens. Granite is very, very common. Basalt is your mafic rock. They're pretty much magnesium and iron, and they're darker because of the iron content. 45% of dark minerals, and then you have calcium-rich plagioclase, but no quartz at all in dark minerals. Okay, and then you have your intermediate rocks, which is an andesite. And these are between felsic and mafic, so they're not quite as dark, but not quite as light. They have 25% dark minerals. The rest is amphibole and plagioclase, and they are associated with volcanic activity along what we call continental margins. And again, we're going to get into more on this, but basically, if you've heard of the Cascade volcanic range in California and Washington and Oregon, we're going to find a lot of this rock there. And then we have ultramafic rocks. These are the darkest of the dark. They're very rare. We don't really find them on the surface of the earth. They're found as dunite and peridotite. Peridotite, some of you may know from Steven Universe, or peridote. Okay, that is the gemstone version of olivine, is peridote. And then you have pyroxene. Okay, these will make up the upper mantle. Okay, so why was I going through all these different types of rock? Because of their texture. Okay, textures are super duper important for rock identification. Texture is based on grain size, the shape and the grain arrangement. You can use texture to determine the origin of a rock, especially volcanic rocks, because you can figure out how quickly or slowly it has crystallizes, and if it is intrusive or extrusive in origin. So the glassy texture occurs when lava or magma cools very, very, very quickly. There is no time for crystals to form before it is completely solid. This is what we call a quenched rock. The entire rock is glassy, and we call it volcanic glass or obsidian. You can also find glass in coarse-grained rocks, meaning if it cooled slowly first, then very quickly, what was left was glass. Vesiculated texture is what we see right here. This is what it means really is that it's a rock with a lot of holes. And it's not like holes like somebody went and dug out a bunch of holes. It's more like natural holes. If you looked at this really closely, it would almost look like the rocks are connected by little webs of rock. It's really interesting. And so the reason for this is because it was ejected from a volcano in a form known as ash or scoria. It can also be due to gas bubbles in lava during its flow. And what these holes mean is that there was a lot of gas that kind of popped. Porphyritic texture means that there are two different crystal sizes, meaning crystals formed at different pressure and temperature conditions. Magma may have paused in its movement upward. Let's say it paused about here. Okay, so right now you're going to have one type of mineral forming. Maybe olivine will start forming, and then it's going to rise further and maybe stop here, right? And in here, you're going to have other minerals starting to form. But what started down here is going to be bigger because it will still be growing. And what's up here will be smaller. These larger crystals are called phenocrysts, but it's because there's two different sized crystals that it is porphyritic, okay? That's all you need to remember here is it porphyritic? I don't know. Are the crystals two different sizes? Do I have really large crystals and really tiny crystals? If yes, it is porphyritic. And this is what it looks like when you cut it really thin and look at it under a microscope. So these are phenocrysts. And these are our tinier and even tinier minerals that started forming at different depths and pressures. And you can see this based on the size, the actual size. You don't even need to measure it. You just know they're much bigger. So the pyroclastic texture is very interesting. Pyroclastic rocks are what we call fragmental, meaning that it's a whole bunch of rock fragments that were ejected during an explosive eruption. And they're kind of glued together, which is what we see right here. So we have this shard of rock, another shard of rock, and we see this in solidified pyroclastic density currents. For those of you who have watched Dante's Peak or any volcano science movie, they usually show a PDC as a fast-moving cloud, right? And this is made up of ash, scoria, and hot gas, okay? But these fragments can also include pieces of lava or what we call lava bombs, which are giant stones that are really hot that get thrown out. And these can all get glued together and form this. This is pyroclastic, okay? We're going to get more into what a PDC is, again, in the volcano lecture. So if you want to look it up, there's a ton of YouTube videos that you can find, but I'm going to show you a couple when we get to that lecture. So the fine-grained texture indicates rapid cooling. It's not glass, it's just very small crystals. Okay, this can occur at the surface, and it's usually where it occurs, but if it's under, it means the magma was quenched right as the crystals were starting to grow. Crystals cannot be seen with the naked eye, meaning you have to use a microscope. Okay, so it is very fine. This is how it looks in thin section. Again, really thin cut rock under a microscope. So a coarse-grained texture indicates the rock cooled very slowly. This happened in the crust or in a magma chamber, like down here. So in the crust or in a magma chamber. This means that the rock is basically entirely crystals, and you can see them. They're very large. It looks like a giant piece of interlocking stuff. And it looks like this when it's cut really thin and looked under a microscope. Pretty, right? Texture plus minerals is what? So texture tells us how fast it cooled. You can figure out if it was stored or erupted. Minerals tell us the composition of the magma during crystallization. For now, we're going to look at this classification chart because that's what all these textures were for. So the top part of the classification chart looks at igneous composition. So is it granitic? Is it andesitic? Is it basaltic? Ultramafic? Does it have these minerals? Okay. And then we have on the left the different types of textures. Is it coarse-grained, fine-grained, porphyritic, glassy, vesicular, or pyroclastic? Okay. We are going to use this in our rocks lab, so you will see this again. But granite is a coarse-grained rock with light minerals. As indicated, it's a plutonic rock, so it's coarse-grained, it's granitic, it happens underground, it probably got exposed during mountain building or erosion. Rhyolite is the fine-grained version of this. It is also granitic, and it means that it probably occurred during an eruption. And you can see here it's very pink, which means it has a lot of sodium in it, just like this granite. And then we have porphyritic granite porphyr, which means it's very coarse. It definitely has two distinct sizes. We see very large pieces and very small pieces, which means that it had two different points where it stopped and crystals started to form. Then we have glassy, which is obsidian. And then we have pumice, which is another type of glassy, but it's called vesicular, meaning it has gas bubbles. And then we have our pyroclastic. These are all our granitic or felsic rocks. Okay, and then we get to andesite, where again, diorite, andesite, porphyr. We have basaltic or mafic, gabbro, basalt, remember, coarse to fine, to two different sizes. And then we have the different vesicular here. We have scoria. So scoria and pumice look very similar, just different colors, right? The major difference between them is pumice can float, scoria cannot. And the reason is because of the size of the gas bubbles and how many there are. Scoria has a lot of very tiny gas bubbles. It also has a lot of iron and magnesium in it, which is what makes it darker. It also makes it easier to sink in water. And then we have breccia here versus tuff or welded tuff. A lot of what this has to do is with how dark it is, what kind of minerals are present. Now we're going to move on to weathering. Weathering is the transformation of a rock to reach equilibrium with its environment. Weathering can be both mechanical or chemical, and the two types usually occur simultaneously, with erosion transporting the weathered rock. Mechanical weathering is the process of breaking down rock into smaller pieces. When this happens, the piece of rock that breaks doesn't change. It still has the same properties. However, what does change is the amount of surface area that is present, which allows for chemical weathering to occur, which does this. So you have a rock that has 4 sides of surface area. It gets broken up into smaller units, 4 of them. Okay, so now you have more surface area, and as it breaks down even more, you have more surface area, which makes it easier for it to break down with chemical weathering. Now we're going to go over some examples of mechanical weathering. So the first one is frost wedging. And we all know what happens when water freezes. It expands about 9%. Frost wedging is a slow, mechanical process that occurs over periods of freezing and thawing. Basically what that means is at night it gets cold enough for ice to form, and during the day it warms up enough for that ice to melt. Water will basically get into cracks in the rock and freeze, expanding and pushing the crack. We can also see lenses of ice, which are really small pieces of ice that will grow within cracks and pore spaces. And this pushing will cause strain, and eventually the rock fails and it breaks further. And this is what frost wedging looks like. So here we have these slightly tilted beds, and what this is, and you have falling rock degree, is that ice has kind of pushing pieces of rock apart, and eventually the crack becomes big enough that the piece of rock can actually fall down. This is also an example of what happens when you put a glass bottle filled with water in your freezer. Please do not do this. You will not enjoy cleaning up all the ice, the fragments of glass afterwards, trust me. Sheeting is when slabs of an igneous body like a laccolith breaks off. Laccoliths form underground where they have continuous pressure. So when it gets uplifted, or it moves up to the surface, pressure is removed. Now the laccolith is trying to expand, and this causes strain on the rock and breakage or failure, leading to separation of outer layers in the form of sheets. This leads to what we call exfoliation domes. Remember, laccolith now is a hard piece. It's a rock now. If it was still molten and it was rising up, it would have the ability to expand. But as it is not heated enough to be ductile, it is very brittle. So as it expands, it breaks, looking like this. And it's pretty cool when you see this. I wouldn't stand too close to something where you can see pieces falling off, because that can hurt. But it is really neat to see. And then we have biological activity. So tree roots can break apart a rock. Burrowing animals will expose rock, allowing for weathering to occur, and decay will form acids that contribute to chemical weathering as well. Chemical weathering alters the internal structure of minerals by adding or removing elements. This causes a rock to change into a new stable material. This makes the outer portions of some rocks more susceptible to mechanical weathering because it'll make it softer, or it'll make it more brittle, or it'll lower its strain tolerance. Water is the most important agent of chemical weathering because it can mechanically weather and it can cause chemical weathering, such as the oxygen causing oxidation, like rust. Carbon dioxide dissolved in water is called carbonic acid, which can melt some minerals and rocks, like limestone. Quartz is very resistant to chemical weathering, so it doesn't actually really get weathered by chemicals. It's going to really be altered by mechanical weathering, which is pretty much due to its high amount of silica. So this is the products of weathering. Quartz will become quartz grains, feldspars become clay minerals, amphibole will become clay minerals and iron oxides, and olivine will rust. What does weathering lead to? It leads to sediments. And what happens to these sediments? They become a rock. So sedimentary rocks, like this one, will form after weathering breaks down gravity and erosional agents transport and deposit the sediment, which becomes lithified or cemented together. This makes up 5% of the Earth's outer 10 miles of crust and 75% of all continental rock outcrops. It is also economically important because it's where we get coal from, or petroleum, or natural gas, fertilizer, and construction materials to make cement. There are 2 types of sedimentary rock that you'll need to remember. Detrital sedimentary rock, which forms from particles weathered from other rocks, and then you have chemical and biochemical sedimentary rocks. Chemical sedimentary rocks form from ions carried in solution, and materials precipitated by organisms called biochemical sediments, like shells and hard parts, is what make up the biochemical aspect. So detrital rocks contain a wide variety of minerals and rock fragments. Clays and quartz are super common. They are distinguished by particle sizes and are very useful for figuring out the deposition environment. So for example, conglomerates have very, very large pieces. It takes a lot of energy to move them, so it's probably that they didn't get moved there by wind. Most likely they got moved by a river. The mineral composition can also be used to classify detrital sedimentary rocks. Chemical sedimentary rocks are usually due to water-carrying ions in solutions. These ions will precipitate as solids to form chemical sediments. These include calcite. Calcite's a big one. And you'll get things like limestone, travertine, you'll get chert, gypsum, rock salt, and coal. And then you have your biochemical, which are from organisms, where you get things like coquina, which are little shells that are very visible. You have fossil limestone, which has you can actually see the shells in it. And then you have chalk, which is microscopic shells in clay. So lithification is the process by which sediment is transformed into a sedimentary rock. Okay, and there's two ways this happens. Compaction, which is when the grains are pressed super close together, reducing pore space. And this is caused by the weight of the sediments on top of each other. They form their own pressure. And it's how more fine-grained rocks are formed. And then you have cementation, which uses water. Water containing dissolved minerals move through the pores, and then this cement precipitates, filling the pores and joining them together. This is significant to coarse-grained rocks, and the common cement here is calcite, silica, and iron oxide. Common features of sedimentary rocks are strata beds, which are layers of sedimentary rocks, and their thicknesses range from being so small we cannot see them to tens of meters thick. Bedding planes mark the end of an episode of sedimentation and the beginning of another, which we can see here. This is a bedding plane. It's basically each of these layers looks different, right? And so we can see them here. And this is how we know that we have different episodes of sedimentation. Basically, maybe this one is 5 million years old, this one is 7 million years old, and this one is 8 million years old. And then we get fossils. Fossils are the remains of life found in some sedimentary rocks, not all. It's important to study the ancient environment, especially in these sedimentary rocks, because not only can we use them to understand what was happening way back then, but we can use them to match up rocks of the same age from different places. So let's say this rock has a seashell that we know to be from the, let's say, Jurassic period. I know this probably doesn't match up. I'm just making up things. And let's say this one has that same one, but this one's missing it. But it has, let's say, a leaf. We can look at bedding from, let's say, Australia, which will have the same things. And we know maybe that this shell was around from 8 million years ago to, let's say, 2 million years ago. But this leaf was only around 7 million years ago, which can tell us that this sedimentary bed is 7 million years old. And this is some examples of fossils. We're going to go over this again a bit more in the future when we get to geologic time, which is going to be in section 2. But this is the types of fossils you can find. You can find imprints, you can find casings of where maybe they've rotted away and all that's left behind is the shape of something. And we also find bones, like Sue, the T-Rex. So here are some examples of sedimentary rocks. The first one is chemical sedimentary rocks. Coquina, we have chalk, which is the hard parts of microorganisms. We have flint, jasper, chert, and petrified wood, which are all microcrystalline quartz, meaning the quartz is so small we can't see it with the naked eye. We have salt, like from salt flats, and I have them written out here for you so you can see them again, because I know that the previous slide didn't have anything written on it, so here are the examples written out for you. Metamorphic rocks are produced when pre-existing parent rock is transformed. This changes in an environment that allow this includes elevated temperature and pressure, changes in mineralogy, texture, and chemical composition. Equilibrium was a new environment. Metamorphism is when a parent rock is subjected to a different physical or chemical environment. This does not occur all at once. It happens a little bit at a time. And this can cause low grade to high grade, which means slight changes to substantial changes. of metamorphism. So here's an example of low-grade metamorphism, where we're going to have shale as a parent. It's going to go through low temperature and pressures, and it'll change to slate, which is metamorphic. Slate is also very brittle, so it breaks really easy. But then we have high-grade metamorphism. So here our parent is granodiorite, and we're going to go through strong compressional forces, high temperatures and pressures, and we're going to end up with gneiss. Gneiss looks very nice. It's very well banded, and the deformation causes layers of segregated material rather than just closely packed. The types of metamorphism that we're going to talk about are contact and regional. Contact metamorphism occurs when rock temperature increases due to a magmatic intrusion. Regional metamorphism is when pressure and high temperature occurs, such as during mountain building. The agents of metamorphism, which you'll need to know, are heat, such as from a magmatic intrusion or burial. This leads to chemical reactions and recrystallization of new minerals. And confining pressure. Pressure is equal in all directions due to burial. This leads to compaction and, again, recrystallization of new minerals. Together, heat and confining pressure can make minerals like garnet. And then we have differential stress, which means pressure is greater in one direction, which is usually due to mountain building. It can cause deformation and development of metamorphic textures, like what we saw in gneiss. And depending on the temperature, rocks can be brittle and break or ductile and bend. You then have our last one, which is chemically active fluids, like hydrothermal fluids rich in ions. This can catalyze recrystallization reactions, dissolve a mineral from one area and precipitate it in another area, and change chemical composition of surrounding rock. Here we have high and confining pressure versus differential stress. So confining pressure allows everything to stay undeformed. It stays in straight lines. Whereas during mountain building, we have deformed strata, which means it'll kind of bend. So low grade and high grade texture. Metamorphism can change texture. Foliation is the development of a flat arrangement of mineral grains or structural features. Characteristic of regional metamorphism, and it's driven by compressional stresses forcing mineral grains to develop parallel alignment, meaning maybe they were all mixed up before, now they kind of go in straight lines and they're kind of bi-mineral. So here we see feldspar and these black bits are biotite and they're kind of all mixed up. And then it goes through differential stress and metamorphism. Now we have straight lines of this biotite and feldspar. So again, this includes alignment of micas, flattening of pebbles, separation of light and dark minerals, which we can see here. Development of rock cleavage. Yes, in metamorphosed rocks you can have cleavage like in slate. However, non-foliated rocks occur when deformation is minimal and the parent rock is composed of largely stable minerals. Okay, so this is foliation. So these are all foliated rocks, meaning that even though you can't always see it, the minerals get sorted. Okay. Non-foliated, like marble and quartzite, means that these are very stable, so they don't exactly separate out like they do in a metamorphic rock, or like in gneiss, for example, which is going to have biotite. So common foliated metamorphic rocks include slate, which does have cleavage, phyllite, schist, gneiss. Okay, so gneiss and schist are very similar, just schist looks kind of crappy, and gneiss looks very nice. So here we see slate in its multiple usages. A lot of times we see slate used as roofs. We also see it as chalkboards. However, slate is very brittle and it will break, and it has cleavage planes. So phyllite is a larger mineral grain size than slate, so it'll have a glossy, wavy surface. Schist is formed regionally by metamorphism of slate, and it is quite schisty. Gneiss is very nice, and it's a banded metamorphic rock with intricate folds. The difference between schist and gneiss is those folds. You don't see them as well in schist. Here we have an example of Vishnu schist and a metamorphically folded gneiss. Okay, so we can see here that we see very clear differences between the mica and the quartz or feldspar. Whereas here, it's kind of all shoved together and you can't really see clear layers or as easily. They're not as pretty. Common non-foliated metamorphic rocks include marble and quartzite. Marble is a coarse crystalline rock which is metamorphosed limestone. So spilling wine on your marble countertop can actually cause them to pit or basically be melted away by the acid and vinegar and a lot of cleaning solutions. But the big one's wine. So when you go to Home Depot, they tend to show the difference when you use when wine gets spilled or different cleaning solutions because of how much acid is in them that will actually eat it away very quickly. And this is why they try to sell you marble countertops that have been sealed, and they recommend resealing your marble countertops every so many years. Quartzite is metamorphosed sandstone, so it's very, very, very hard. And so it's really used a lot for building materials, and it's really cool. It's usually pink. But sometimes people have trouble seeing the difference between quartzite and marble. But if you take the time to really look at them, you'll see it. So one of the biggest examples of marble being used in infrastructure is actually the Taj Mahal, which is something that has come in with global warming and people worrying about acid rain is, will the Taj Mahal eventually melt away due to the acid slowly pitting and eating away the marble? But yes, this is one of the world's landmarks. I believe it is one of the wonders of the world. It is really beautiful, and I recommend if you get a chance to go see it, that you do. Anyway, this is the end of our rocks lecture. I hope that you enjoyed it. Please make sure to re-review it if you see things that you missed. So this way you can fill out your study guides, and have a great day.